do something new here. Something like that. Existing model, dimerization, new workflow. Model expiration. Okay, let's try this again now. I will close this one. See if this helps. Okay, yeah, it seems to be using another port right now. So, but now it should be fine. At least it should. The scheduler should be a different port. Okay, great. Sorry for that. So we have then a Dask client, and the Dask cluster consists of a Dask scheduler that is hosted on this address. And here we can see some information about the cluster, for example, the number of workers that we have and the number of cores and the memory, etc. There's also a dashboard, but currently we don't have support for showing this, but I hope we will have it soon in the future. Right, so the next thing we need to define is the how we would like to sample parameter points for our model expiration parameter sweep. So Sciop comes with different kind of designs and priors to do this. And so I will show you here how you can use design. So it's experimental designs. And there's a famous method called Latin Hypercube sampling, which basically is a space filling design that will create very nice and even distributions of points in a defined space. In here, I just use this default parameter expression that I showed you before. And I can actually reduce this a bit now in case it hurts. So here you just define your bounds for that space that you like to sample. So the min and max. And then you can pre-generate some sample points from that, but this will actually not be computed immediately. It's a lazy computation. So once we actually call compute on this, then it will sample those points for us. And also we need some features to represent, or summary statistics to represent our time series. And Sciop comes with a third-party software called TS-Fresh. TS-Fresh is basically a database to extract several hundreds, if you like to, different types of time series features, such as autocorrelations and fast Fourier transform, you name it. They have basically everything there. And they have sort of different sets that you can choose. And Sciop has included these sets so that you can basically generate features without knowing what kind of feature would be good for this problem. So here I would use a minimal set, which will be the default if you use TS-Fresh. And if we look at the summary, oh, now tab works, great. Dot features. We can see here that the features that I will demonstrate here, in this case, is sum values, median, the mean, standard deviation, variance, max, and mean. But you have several hundreds of supported features that you can compute. So this might not be the best feature set for this particular problem, but this is just a demonstration of the workflow. So let's just continue with that. So then we move on to the actual model expiration toolkit. And this is named by StochMet, which stands for this Stochastic Model Expiration Toolkit. But it's not really restricted by stochastic simulations. You could use this for deterministic simulations as well. But to create this class that we will use, you use StochMet, and then you provide the simulator the Latin Hypercube design that we had up here. We named it LHC, and then the summary stats. So we call that, and then the first time it may take a while because it's building a lot of things for it. It's actually constructing lazy computations for us in Dask. Okay, and then when you like to actually start this sort of parameter sweep, we just called met, as I called the instance of this class right here, .compute, and you decide how many points you would like to sample from the Latin Hypercube. And then you can also specify chunk size, and this is related to how you partition the data into tasks when signing it or submitting it to the scheduler in the Dask cluster. So basically it's just create partitions of the data instead of having each parameter point being one task when we distribute the work. So here we will use 10 instead in each task. So let's compute this. Let's hope it doesn't run too long. Right here is just some configurations that we can add to the data class inside StochMet, just for convenience for visualizations. So nice, it's completed. Not very important, but could be nice. This is mainly for us to sort of keep track of a list of parameters, species, etc. And here is really where the sort of more sophisticated things start to happen. So what we like to do here is that we use the features, the summary statistics, to represent the qualitative behavior seen by the model. And what we like to do is to visualize this information to the modeler. And we do this by doing a dimension reduction on the feature space. And to do that, we have implemented several methods, some very common methods such as PCA for linear dimensional reduction. We also support TISNI, which is a popular method to do nonlinear dimensional reduction, as well as UMAP, which is also a nonlinear dimensional reduction method. And I usually prefer UMAP because it's much faster. So to do this, we start met.explore and we specify the DR dimension reduction method that we like to use. And what we will see here is just a prototype of the type of interactions that we would like to provide to the modeler. So this showcase right here is just a prototype, but the aim is that we will implement this directly inside StochSS Live, so that you will have a user interface directly that looks something similar to this. And what we are looking at here is the reduced dimensional space of the feature space. And it's important here that this is not associated to parameters, it's feature space we are looking at. So the intuition is right here that points that lie close to you can see every point here as one parameter sample. We have simulated that, we computed the features, and then we did a dimensional reduction on those features, and that is the space that we are looking at. So the intuition is that points that are close to each other should have a similar behavior, a similar qualitative behavior. So if we click some of these points right here, we can see, actually, when I switch the Jupyter Notebook, now shows 100 trajectories. So that's a bit inconvenient because it will be very hard to actually look if they are different. But anyway, this is how you could do it if you have several ensembles of trajectories per parameter points. Yeah, just have a look here and press another one right next to it, and you can see all the trajectories associated, all the simulations for that point there. And you can study this behavior in this way. Let's actually do this quick. Shouldn't take long. One. Like that. So this is a way to sort of explore the feature space. So you can find different qualitative behaviors by inspecting different clusters. Now we only used 100 points here, so might not show that much. But imagine that you have several thousands or tens of thousands samples that you would like to explore. This sort of helps you to navigate that data in a good way. And let's see if we can rerun this now with just one trajectory per sample. Might be a bit easier to navigate. So let's zoom in here. So now you see it's only one trajectory. And then we can start exploring different points here. And you can see here that they are very similar to each other, even though they come from different sampled parameter points. So let's say that you're interested in this particular behavior right here. What you can do is assign a label to those. Label 1, submit. And then we have labeled those. And let's, for example, say that we like to explore this little cluster up here. You can then interact with those, look at how they look like. And as you can see here, they are very similar as well, but quite different from the previous one in this way. Okay, and then you say, but this is a different behavior, so I would like to label this differently. So I give it a label of 2 instead. Now you can see we have a unique color. So everything that is purple is non-labeled, and everything that has another color is labeled. So if you imagine this being like you having tens of thousands of points, for example, you can't possibly go and label everything, right? So this is where we start using machine learning again for semi-supervised learning to infer the labels of unlabeled data points. So basically you could use this to label the other ones right here that is not labeled, but you can also use it as a downstream process where you use the semi-supervised learning model to basically filter out even larger parameter sweeps by saying, yeah, this one belongs to this cluster. So then you maybe just want to keep that cluster, that label, that particular qualitative behavior. So to do that, we have a method called label propagation implemented inside Sciop. I won't go into the details because we don't have time for that. But basically, it's a semi-supervised approach, and it should label the points that are not labeled based on the information that we gave to the modeler. So using this, we sort of have an implementation of semi-supervised learning, but using an active learning approach where we basically request feedback from the modeler to give labels to the data that to clusters that is potentially interesting, a cluster that contains potentially interesting qualitative behavior. And just to show how this looks, you can then take, let's just compute it on the same data for label 0 right here. And then we can do it again. But this time UMAP is actually non-deterministic, so it might look a little bit different, but usually it's very consistent. So it labeled this all as containing to that cluster. If we take another one here, the other label that we took, we can see how it, then it labeled these ones as belonging to that cluster. So a really bright color right here in yellow means that it's very certain that it belongs to this cluster. And the ones here, they are very certain, the model semi-supervised learning model is pretty confident that these do not belong to the corresponding cluster. So this is a way to sort of navigate model exploration and to use it later for downstream processing. So a way to train a model based on what you think as a modeler is an interesting behavior. Okay, now I think time is running short, maybe. Let me just close that client that we had and move on. So next I will demonstrate model parameter inference using Sciop. And I will try to be a bit more quicker here because the actual backbone of the workflow is very similar to model expiration. So we define here, once again, an auto-generated Jupyter notebook is created. We create the associated imports, the model. Once again, it's the same model we're working with. We define our simulation configurations, and let's change that to 1 to make it more faster. And then in model inference, we need these, but I won't say so much about that. So there are 4 things we need for model expiration. We need the prior or some initial design. Usually in inference, we use a prior of the parameters. We need the simulator. We need to extract some features, or as it's usually called in parameter inference, it's called summary statistics. And we need some kind of distance to compute the discrepancy measure between observed data and the simulated data. So first, let's create some fixed data. So just now I will use some synthetic data taken directly from the model. So I just do the same as I did in the previous one when I run it, and then you could plot it, for example, if you like. Here I just reshape the data to fit for Sciop. Then the next step is to define your prior. So right here I will use something implemented in the Sciop, a uniform prior, where I simply just take the bounds to be some distance away from the default value inside the model. So you have the uniform prior right here, uniprior. You define the simulator, and here we have shown that in the previous, for model expiration, I showed you the wrapper functions that we had. Here is a more explicit way of doing it, where you can sort of define whatever kind of simulator you want. We call the model.run right here, but before that, we call this function to set the parameter values inside the models directly. And this is just a way for you to sort of, if you want to maybe pre-process the data in some way, pre-process the simulations in some way, or maybe you want to catch some errors or whatever. This is a way to do it. And then finally, I just wrap this function with the simulator 2 here, because Sciop requires that the simulator only takes 1 argument, which is the parameter point. We define summary statistics in the same way as we did in model expiration, using the default minimal set of TS-fresh features. And then we compute a distance here. We have several implemented distances in Sciop. We have Euclidean distance, which is the most usual case. But here we also have the square distance. Once again, let's try to see if we can create this client. It just complains here that it's a different one running on a different port. So now we have that client again. And here actually starts the final inference part. So we use the class ABC, which was actually implemented up here. So sciop.inference.abc inference, import abc. What you have to provide then is with your observed data, which I call fixed data here, your simulator, the prior function, summary statistics, and the distance function. You could also give this threshold that I mentioned before, because we need to accept samples based on some threshold of the distance. So you can do epsilon equals 0.5. Let's take a really big one now because we want this to be fast. Actually, ABC is very slow. It takes quite a while to converge, depending on your prior, of course. Here we then just compute the summary statistics for our observed data. And here finally we call infer, which basically just do the inference for us, where you decide how many samples, approximate samples you would like from your posterior. The batch size is basically how many runs we continue in the loop to run before. So you just do a batch simulation and look at how many get accepted of those. And the chunk size is similar to model expiration, where you sort of partition your data for tasks into the task scheduler. 100 shouldn't take that long, I hope. No, good, went fast. And then you can do whatever you want with this. If we have a look with the res file here, and it's a dictionary. So if you take the keys out of this, you have all the accepted samples, which should be of dimension 100. We wanted 100 samples. All the computed distances, all the accepted count, and the number of trials, which is basically how many proposals that we needed to converge to 100 samples. And then the inferred parameter, which basically is the expected value of, or it's the empirical mean of our samples right here. So then you can do whatever you want. You could compute the mean absolute error. You could plot the number of sample as a histogram, etc. Currently, we don't have any implementation for visualizing this, but I hope it will come soon. And then you can compute that inference, and we got a pretty bad score here at night, but that's no point with this. I just want to demonstrate the workflow. So just one final thing to mention is that here we just use regular ABC, which is the most vanilla version of likelihood-free inference. However, in Sciop, we have several versions. .inference. So we have SMC ABC, which has better convergence. We have another replenishment SMC ABC. Here is the latest version that we have, which is the Bnn Inference, which uses a Bayesian neural network to, first of all, it learns features, the summary statistics automatically by a neural network, and it's able to directly give us an approximate posterior from the neural network. So it's a very neat method and requires very few simulations compared to, for example, ABC and even SMC ABC. We also have inside our models here, we have different machine learning models, classifiers and regressors. We have a CNN, convolutional neural network, that can learn summary statistics. However, you need to simulate data to actually learn, of course, the summary statistics from the data using a convolutional neural network. And then you use that convolutional neural network as a summary statistic in a rejection scheme. So similar to what we do here in ABC. However, in the BNN, it can sequentially update, do Bayesian updates from the data directly and give you a posterior directly. Okay,